In the previous module, we have seen the visualization of Fourier series representation of periodic signals. Let us write the expression once again. So the Fourier series representation of periodic signal are given by xp of t equals to summation k ranging from minus infinite to infinite ak e to the power j k times omega naught t. So let me have a quick recap of these terms. Here ak are the coefficients of the Fourier series. The k here is an integer, or it represents the coefficient number. K times omega naught is the harmonic component or the harmonic multiple of this fundamental frequency omega naught. So the omega naught here, let me emphasize that once again, omega naught is the fundamental frequency given by 2 pi by t naught, where t naught is the fundamental period. Now we all deal with real signals in real world. So let's try to modify this expression, or let's try to see how this expression turns out to be if the signals are real in nature. That means if xp of t is real, like a cos signal or a sine signal or any real signal that we want to approximate using Fourier series, if xp of t is real, then you can see that from the expression, in general we can represent any periodic signals. So xp of t can be a complex signal also. But if in case xp of t is real, xp of t and its complex conjugate will be equal. Just because a signal is real, any real number and its complex conjugate is equal. So if we have xp of t to be real, we can have xp of t equals to xp of t complex conjugate. I am representing that with a star. So what does this mean? If xp of t is real, of course the signal and its complex conjugate would remain the same. Now let's impose this condition in this equation. So if I rewrite this expression, now before rewriting this expression, let's see what is this xp of t star. That means the complex conjugate of xp of t. So let me write that xp of t star, what is that going to be? It's a complex conjugate of xp of t. You can see that from here, if I take complex conjugate of this summation, it is going to be complex conjugate of ak and the complex conjugate of this exponential term. So that is going to be equals to summation k ranging from minus infinite to infinite ak complex conjugate times e to the power minus j k times omega naught t. Just because we need to represent a complex conjugate signal, we are simply making the individual terms as complex conjugate, and therefore we have ak star and e to the power minus sign here, just because this is a complex conjugate term. Now this expression that we have obtained, let us rewrite this expression in some different form. What I'm doing here is I'm making a change of variable here. I will be replacing minus k with some variable, let's say it is k dash, or with the help of change of variable in this formula we can obtain a new expression as xp of t star is going to be equals to summation. Now k is replaced by minus k, you can say. So I am making a change of variable here. So you can have k, as the k is replaced by minus k, or you can say minus k is replaced by k, the change of variable there. So this summation won't change. It will be, instead of running from minus infinite to infinite, it will run from infinite to minus infinite. So this remains the same. There's a change of variable here, so I will write it as a minus k star e to the power j k omega naught t. Now what I have done here is simply a change of variable. Now I will compare these two expressions. Now let me compare this expression here. Let me write that expression number 2 and let it be compared with expression number 1 here. If I compare both of these expressions, you can see that for real signals, as we have xp of t equals to xp of t star, these two expressions, equation 1 and 2, must be equal. And if they are equal, you can see by comparing the coefficient, ak must be equals to a of minus k star. That means, let me write that, ak must be equals to a of minus k star, and this is true only for real signals. So this is very fundamental result that we have obtained. Now let us try to understand this. What does this mean? AK, as we have seen, are the Fourier series coefficients, or the factor, the scaling factor of the complex exponentials using which we are trying to represent the periodic signal. And we have imposed the condition of xp of t being real. So we have, for real signals, ak equals to a of minus k star. It means that the Fourier coefficient for real signals for certain value of k is going to be the same as that of the Fourier coefficient at minus k. Only change is going to be in the complex conjugate. It is going to be the complex conjugate of the term that is at the kth location. So this k is nothing but the coefficient number, the Fourier series coefficient number. So let me try to make this k as an axis. So you can visualize this k as an axis, just because this k is a number or the index of the complex exponential. This k is an integer, so we may have this k value as 0, we may have k as plus minus 1, we may have k as plus minus 2, and so on. So for real signals, we have made the conclusion that this ak, suppose this k is 1, it is going to be the same as that of minus 1. So these two signals are going to be equal. These two coefficients are going to be equal. The only change will be there in the complex conjugation. So the term here is going to be complex conjugate of this term here. That is what this ak equals to a minus k star indicates. So these coefficients are available in pairs, you can say. So 1 and minus 1 forms one pair, 2 and minus 2 forms another pair, and these coefficients are available in complex conjugate pairs for real signals. So you should note that this is true only for real signals. Now let's make use of this expression or this condition that we have obtained here and try to see how this expression is changing if we impose this condition here. So let me go to the next page and let's see what we get if we impose such condition here. So let me write the expression once again. Xp of t, that is a periodic signal, is given by a linear combination of complex exponentials. So ak e to the power j k omega naught times t. And for real signals, we know that for real signals we have ak equals to a minus k star. Now let's split this summation and express it in some different form for convenience. So what I'm doing here is, as we have this Fourier coefficients available in pairs, I'll be simply collecting those terms together. So what I will do is to isolate these individual terms of AKs. So I'm rewriting this expression in a different form, something like this. Say xp of t is going to be equals to, first I will write the term at k equals to 0, the middle term, as we have seen here in the previous slide. I'm first indicating the 0 term here, just because it is a lonely term there. I will write that first. So I'll write that as a naught, just because k is 0, the exponential to the power 0 is going to be 1, so there's no other term there, plus summation k running from 1 to infinite, and inside this brackets I'll write ak e to the power j k omega naught t plus a minus k e to the power minus j k omega naught t. So what I've done here is to simply represent this xp of t in different form. I've isolated the 0th component, and I have kept these coefficients, the complex conjugate pairs, in these brackets. So this expression here is the same as that of this expression, the original expression. I have only modified, or I have simply rearranged this equation. Now we know what is this term. You know, this ak and a of minus k are complex conjugate of each other. So a of minus k can be represented as a complex conjugate of ak. So what I can write here as equals to a0 plus summation k running from 1 to infinite ak e to the power jk omega naught t plus ak star, or the complex conjugate e to the power minus jk omega naught t. I can do that very well just because ak and a of minus k are complex conjugate of each other. Now let's observe this expression that we have obtained here. This term is exactly the complex conjugate of this term here. You can see that the first term in the bracket is exactly the complex conjugate of the second term here. So these two are complex conjugate. Let me write that they are the complex conjugate of each other. If they are complex conjugate, we know if two terms, if they are complex conjugate of each other, and if we add them together, what is the resultant going to be? See, if I have a complex number, if I add that with its own complex conjugate, we are going to get twice of the real quantity. So this is going to be equals to a0 plus summation k equals to 1 to infinite. This is going to be twice of real part of ak e to the power jk omega naught t. Just because these are complex conjugate of each other, if I add them together, we are going to get twice of the real part. Now let us look at this ak. What is ak? Ak, as I said, is the scaling factor or the Fourier coefficients, the scaling factor of these complex exponentials. Now the scaling factor can be a complex value in general. This can be a real value as well as it can be a complex value. It can be any scaling factor. So in general, let us represent this ak with the help of a complex number as ak e to the power j times theta k. So I've considered this ak as the Fourier coefficient that is being represented in a polar form. So there is a magnitude that is capital AK and there is a phase that is theta k. Just because AK is a complex number, it will have some magnitude as well as phase. So I've taken a generic case of this AK being represented as capital AK e to the power j theta k, where capital AK is the magnitude and theta k is the phase of this AK. So the resultant expression is going to be equals to a0 plus summation k equals to 1 to infinite twice of real part of e to the power ak times e to the power j k omega naught t plus theta k. Now this is going to be equals to, therefore xp of t, the resultant expression is going to be equals to a naught plus summation k equals to 1 to infinite twice of, I'll take 2 common, and you know what is the real part of this? The real part of this is going to be equals to a k cos of k omega naught t plus theta k. The expression that we have obtained is called as an alternate representation of Fourier series. So let me emphasize this expression that we have obtained here. So it is the Fourier series representation for real signals. So you can see that there is no complex part involved here. Everything is real. So this, for real signals, this is an alternate representation of Fourier series for real periodic signals. Now as we have considered this AK in a polar form, we can also represent this AK in a Cartesian form. What I mean to say here is AK can also be, so here if AK is represented in the polar form, we get this expression, but if AK is represented in Cartesian form, say some BK plus J times CK, then the expression, you can work out that this expression turns out to be equals to xp of t equals to a naught plus 2 times summation k equals to 1 to infinite bk cos k omega naught t minus ck sine k omega naught t. So these three expressions that we have obtained here are the same. So this expression that we have newly obtained here is the same expression that we have obtained it earlier, but in a Cartesian format. So here this expression, this expression and this expression both are the same. I have simply made use of different representation of this ak. If I represent ak with an exponential or with the help of polar form, I get this expression, and if I represent this ak in a Cartesian form, I get this expression. Both of these expressions are equivalent. So these are the expressions of Fourier series representation of real periodic signals. We shall see more into this in the next module. See you then.